Hello and welcome to another episode of Chemistry from Jay's House. So today we're going to be talking about acids and bases. So the first thing I want you to do is I want you to pause the video and get ready to take notes because there's actually going to be notes. So make an acids and bases notes file in your chemistry folder on your drive. So find your chemistry folder, find all the other chemistry notes, make a new document. Please call it acids and bases notes and pause the video to do that now. Welcome back. Clearly you followed my instructions and you now have an acids and bases notes document. Now in that document you're going to take some notes. We're going to be talking about acids and bases. So at the top, in the middle, let's write acids and bases. That's the unit title. And that is just a smidge off, isn't it? Well, you can read it. Good enough for government work, eh? Before we get into actual notes and everything, I want to talk a little bit about the history of acids and bases. We've known about them for a long time, all the way back to the ancient Greeks and that sort of thing. And we knew that stuff came in kind of two different flavors. Actually, I guess three. The one flavor is it doesn't do anything. It's like wood doesn't do anything. Metal doesn't do anything. Water doesn't do anything. But there were some things that we noticed tasted sour if we tasted them and corroded metal. And that meant that if you put it on metal and you walked away for a little bit, weird. It would like eat away at the metal. And we gave it the name acid. So before we had, litmus tests and the chemistry behind it all, we would taste it or we'd put it on metal, and if it tasted sour or corroded metal, we called it an acid. And there's a whole nother substance that didn't taste sour. It tasted bitter, much like me. So bitter. And we noticed we're kind of slippery. And when I say slippery, I mean like liquid soap slippery, as in you put it on your hands and you're like, oh, it's kind of like still on my hand, like butter, right? It's like, it's kind of hard to get off. It's slippery. And we said, hey, we're going to call those bases. And we noticed that if you put these together, they stopped each other. As in, if you put some acid on a metal and it started to eat it away, if you threw a base on top, it would stop eating the metal. So we've known about acids and bases, and we've known how to categorize them for a really, really long time. And then chemistry came around and we figured out how it works. So we're now going to jump into how it works. But it's worth pointing out that we've known about them for a long time. So now into notes. So clearly you have your acids and bases notes document still open. I didn't assign homework because there wasn't homework and it was spring break, woohoo. I didn't collect homework because there wasn't homework, but I know what you guys are thinking. Jay sure talks a lot, but I hope you yelled, what's the point? Let's see, I believe you're going to be doing this on the 20th, so this date might be wrong. Check an actual calendar, please, to write the correct date, but I'm pretty sure this is slotted for the 20th. And then skip the line, go all the way left, and write the point. Hey, it kind of feels like class, doesn't it? It feels like we're still in my stinky classroom. And why do acids convert water into hydronium ions? It's supposed to be underlined, not crossed out. There it is. I'm not refilming for that. So we realized early on that, especially as acids get more and more intense, maybe we don't have metal available, or maybe we don't have lab assistants who are willing to taste it. How are we going to define an acid? Is there a way that doesn't require it to eat metal or to taste it and get down to the chemistry of it all. And we said, yes, there is. Hey, we've noticed some stuff. So first, I'm going to leave that up there for a moment while we take the note of acid. So the way we define an acid, is something an acid or not, is we ask, how does it affect water? So an acid is a substance that donates protons comma or hydrogen ions which is written as H with a little plus. It's a positively charged hydrogen ion in aqueous solutions. Aqueous means water. So you throw a substance in aqueous solutions, you toss it in water, and you find out, is it an acid? That's what this is saying. We should probably find out what a hydronium ion is, because that's, up here in the point. Hydronium ion, it's a nice short note. Hydronium. Hydronium ion, whoops, forgot the word ion. These things happen. Is simply H3O+. That's it. It's a chemical. Like water, which is H2O. A hydronium ion is H3O+. So you toss an acid into water, and if you get some of these, you're an acid. If you don't get some of these, you're not an acid. That's basically the topic today. So please pause the video, take this note, because I'm about to erase the entire board. And when you have these notes down, start the video back up. Pause. Okay, welcome back, because clearly everyone did exactly what I said, because you guys always do absolutely everything I say. Send me $40 now. So, what does all this mean? Scientists are two things. One is lazy, and the other is they like to be super accurate. So let's say you got some stuffs, and you go, I wonder if that stuff is an acid or not. Now, one thing I could do is I could put it in my mouth. Terrible idea, but, it's a possibility. If it tasted sour, I'd be like, yay! As I die, I was right, it's an acid, and then I'm dead. Or I could throw it on metal and watch. But that doesn't seem super accurate, and that doesn't explain strength, like strong acid versus weak acid and all this. So we'd like to be more clear about it. So let's say I have this stuff, and what scientists realize is, well, throw it in water. Okay, so if I throw it in water, so here's the stuffs, and there's water kind of floating all around. It's a water thing, and water spins. And just be clear, there'd be water in front of it, there'd be water behind it, because we live in a three-dimensional world. So I throw the stuffs in water, it gets surrounded by water, and I wait. That's it. I just wait, and I start testing all these things. Now, if all of the water there stays water, it all stays H2O, right? So it's, looking at it, it's H2 because there's, two H's, single O, and scientists don't write the one. It should be H2O1, but scientists are lazy, so they just leave all ones off. So if everything stays as H2O, well then, guess what, buddy? You're not an acid. Get out of here. But if some of these start converting from an H2O into an H3O+, see a lot of similarities, especially if I turn this upside down. Yeah, there's a lot of similarities there. We'll talk about those in a minute. If some of these start converting from H2O to H3O plus, then lo and behold, you're an acid because you changed water into hydronium. Crazy. So now let's talk about the chemistry behind that. But that's the idea. That's what you are, an acid. You get the fun name acid. We can actually, toss that term around, and you're no longer not, glob, and you are now acid if you change water into hydronium. So let's talk about that a little bit. Well, here's the cute little printout. Water plus a proton gives you hydronium. Ooh, isn't that nice? Let's talk about that for a little bit. Now, there it is. Pause it if you need to kind of read that. And I'm just going to leave that up there. Actually, I'll put it down because then it'll be slightly larger because of forced perspective. Okay, so what that says is if you have water, dink-a-dink, and you have a proton held right side up, dink-a-dink, that somehow you get hydronium ion. Wait, what? That seems a bit like magic. If I have water and I add a proton, I get hydronium ion? Why is that? Well, that's when we go, oh wait, what's a hydrogen? And I love this. I printed it out because there's a wonderful typo there. And I just shouldn't have, but I printed it out because I love the typo. So this is an image from the internet. What is a hydrogen atom? Well, a hydrogen atom is something that has a single proton and a single electron. So a single proton and a single electron makes a hydrogen atom. And that is in the top left of the periodic table. It's the smallest atom there is because if you remove the one proton, you no longer have an atom. So a hydrogen is simply a proton with an electron. And this doesn't have a charge, right? Because you have one positive, one negative. They cancel each other out, just like acids and bases. So this is a hydrogen without a charge. But what if you have just a single proton? What if we take the electron away? Well, a hydrogen is anything with a single proton. So what's a single proton? Technically, it's a hydrogen atom. And this is where it gets kind of annoying. And the reason it gets annoying is what we should say is if you add a proton to water, you get hydronium, right? If you take water and you add a single proton, you get hydronium. But the problem is chemists believe that absolutely everything in this universe, appears in the periodic table. If you break it all down to its smallest bits called atoms, that it would fit somewhere in our periodic table. And if it didn't, we'd just change the periodic table to include it. The periodic table should be everything. And this, a single proton, does not exist, doesn't have a fun name. Unless we go, hey, wait, that isn't just a proton. What if we called it a hydrogen atom without an electron? And we would write it as H+. It's a hydrogen atom because every atom that has only one proton is a hydrogen atom, but it's without its electron. Normally we see hydrogen like this, where it has its electron zipping around. There's no charge here. This one is just a proton, so it has a positive 1 charge. That's why this should be H1 plus 1, but scientists are lazy, so they leave the ones off. So it's just an H+. And we say, if we call this proton, which technically is just a proton, but if we call it a hydrogen ion, now it fits on the periodic table. Doesn't that feel nice? Doesn't that feel nice that protons now exist. A single proton can now exist because it fits on a periodic table, as long as we change the name from a single proton to a hydrogen ion. Technically a positively charged hydrogen ion, but a lot of times people just leave the positive charge off. So, but wait, if that's, I noticed something. I just noticed that if we think of water plus a proton, which is a positively charged hydrogen ion, what if we think of water, which we know is H2O, and we add, instead of calling this a proton, let's call it an H+. Well, doing kind of fake math, well, I have two hydrogens and I add a hydrogen. 2 plus 1 is, let me get a calculator. I believe that's a 3. And one oxygen here, no oxygens here. 1 plus nothing is, where did I put that calculator? A single oxygen. And no charge here, positive 1 charge here. Nothing plus positive 1 equals, there's the calculator. H3O plus. Hey, there's a name for that. That's called a hydronium ion. So this right here, water plus a proton, gives you a positively charged, that's the plus, for some reason they write it on the atom instead of above the atom, gives you a positively charged hydronium ion. Just says that the math, this kind of fake math, that H2O plus positive H gives you H3O plus. Whoop-de-doozers. So what that means is the way to find out if something is an acid or not, what are you crazy stuff, is throw it in water. And if it starts donating protons to water, then it's an acid. So let's see that visually. Remember, if I'm erasing stuff too quickly, you have a pause button. Use it. So again, let's reset. Let's say I've got gobbledygook. I don't know what this stuff is, but here it is. I put it on. And I go, I'd love to know if it's an acid or not. Well, let's throw it in some water. Let's throw it in an aqueous solution, which just means a solution that has water in it. Okay, and the water flops all around. Now, if I throw it in the water and this is all I get, just green junk and water, no changes, then guess what? You're not an acid because you left water as water. Now, what if this stuff starts donating protons? Dink. Oh. And it donates a proton over here. Dink. Oh. And, I noticed that the teacher keeps putting the protons at the top. I wonder why that is. Let's see. We have a positive proton. We have this water with the positive bottom and the negative. Oh, I bet the positive sticks to the negative end. Donk. Donk. You see, that's just magnetism. Oh, yeah. And if we think of this as a positively charged hydrogen ion, right, instead of a single proton, if we think of that, then we end up getting this. So the orientation is the same. Oh, okay. So if I add a single proton to H2O, and it'll stick at the top, right, because positive charge clicks onto the negative end of water. Oxygen's electronegative. It's the, Endgame, Avengers Endgame. It clicks on there, and we get this kind of a dealimaboober, right? Then every time a proton sticks to a water, it's no longer H2O, it's now H3O plus. It's now a hydronium ion. Oh, there's another one here where it donated a proton, water took it, and it's now a hydronium ion. So the way chemists check to see if are you an acid or not is they just toss it in with water, and then they check for this. So right now, if I used other chemicals to say, hey, are any of you hydronium up in here? It'd be like, bing, I'm a hydronium. Bing, I'm a hydronium. And then the chemist goes, aha, well then you get the name acid. Ha 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 ha. But if we take, reset. If we take a substance and we throw it in the water and the chemist asks, okay, are any of you hydronium ions? Did this substance give any of you a proton? And they'll go, no, we're all just still water. You can kind of see here. Then it goes,